Dear participants, a very good afternoon and welcome back to the second session of day 2, which is delivered by the very renowned personality from Delhi Technological University, none other than Dr. Ajeet Kumar. And today, Dr. Ajeet Kumar sir is talking on application of specialty optical fibers and waveguides. I request one of my colleagues, Mr. Maruti Kumar, to introduce today's session's resource person, Dr. Ajeet Kumar. Kumar sir, please.
Thank you, sir. Hello, everyone, and welcome to today's session. It's a great pleasure for me to introduce our speaker, who is going to talk to us about application of the specific specialty, optical fibers and the waveguides. Dr. Ajeet Kumar was born in 1983 in India. He received the BSc degree from Deen Dayal Upadhyay Gorakhpur University, Gorakhpur, India in 2002. The MSc degree from the Indian Institute of Technology, Roorkee, India in 2004, and the PhD degree from the Indian Institute of Technology, Roorkee, India in 2009. He was a postdoctoral fellow in the Gwangju Institute of Science and Technology, JIST, Korea. In July 2010, he joined the Delhi Technological University, Delhi, where he is currently an assistant professor. He has published more than 100 research articles in journals and conferences. His current research interests include novel large mode area single mode fibers, segmented cladding fibers, fiber optic sensors, and waveguide long period gratings. Dr. Kumar has recipient of the Young Scientist Award by Uttarakhand Government, India. He is a life member of Optical Society of India, Indian Laser Association, and the Indian Science Congress Association, and the member of Optical Society of America. Ladies and gentlemen, please join me to welcome Dr. Ajeet Kumar sir. Welcome, sir.
Thank you so much for such a nice introduction. And before I proceed, I would like to thank the organizers to once again inviting me for this FDP program, which is sponsored by the AICT, and especially Dr. Yadav for having so kind for every time and whenever you need any information or any kind of thing, so he always be there. So thank you so much for once again inviting me. And what just yesterday I requested Dr. Yadav to have all the schedule, and I have seen so nice speakers you have arranged, and that will be really good for all the participants which are going to spend 1 week time for this Atal FDP program. So today, in today's talk, I'm going to talk about the more on research things. So I will try to, my motive will be to start from the scratch and see how the scientists who are working in the field of simulation are coming with the design, and what care we should always take if you are working in this particular field. So we'll talk about something we have just listened. It is basically about the specialty optical fiber. So let me share my screen. This entire screen. So I think my screen is in shared mode, right? And is it a full screen? All right.
Yes, sir.
Okay, fine. So we are going to talk about a topic which is application-specific specialty optical fibers and waveguides during this AICT training and learning program, and which is 1 week FDP program. I think maybe it's the second time you are organizing, because last year we have been here in the maybe in month of November. So we are going to talk about modeling of the fibers, which can be used for some spatial applications. So we are talking about the specialty optical fiber. Before we go to the specialty optical fiber, I will take some time to explain what do you mean by the conventional fiber briefly, and then we'll see what are the limitations of the conventional fiber and why we need to go for some spatial design. So, what is the conventional optical fiber? Conventional optical fiber is basically a design which guides the light up to desired distance by the process which is called total internal reflection. So, you already know that in case of optical fiber, the light is you have a core and cladding, where the refractive index of the cladding is slightly less than that of core. Usually a difference of n1 minus n2 is the order of 0.01, and by the process of total internal reflection, the light which is launched in the higher index medium, which is guided through the multiple reflection. So this is a schematic diagram of a step index optical fiber. The refractive index profile of this fiber is something like this. In the core region, you have refractive index N1, which is the constant one, and in the cladding region, you have the refractive index N2. So this is the, you can say, the refractive index profile. This is a typical refractive index profile of any conventional optical fiber. This conventional optical fiber, you know that majorly it is used and it was designed or invented for the long haul communications. Means long haul communication means you can send the signal, from one place to a very large distance place with a very less propagation loss. You cannot say that you don't have any loss, you always have the loss, but you always want to minimize the loss so that you can send the information at a very large distance. So this was the uh, one thing for which the conventional optical fiber was designed, and later on the number of application has been seen for the optical fiber, and that comes through the specialty optical fiber. Now, what are the points which we will talk about the conventional optical fiber? If there is a conventional optical fiber, you know that uh, there is a term which is called dispersion, and you will discuss in detail in the second section of my talk what is the dispersion and how we can address with this particular issue. So you know that you always, if you want to, send the signal from one place to the another place, and uh, you want to avoid this kind of thing which is called dispersion, or minimize this effect dispersion, you try to operate your sender signal near to zero dispersion wavelength. But zero dispersion wavelength in the conventional fiber is at a wavelength which is 1310 nanometer. All right. And in the first point I have mentioned about the optical fiber or waveguide is the material which can send a signal up to a desired length with a less propagation loss. Less propagation loss means you have to talk about a wavelength where the propagation loss is minimum or close to minimum. That is why the we have the propagation wavelength or communication wavelength which is close to the 1550 window. So at 1550 window, we don't have a minimum dispersion. So now you have to send a signal close to the 1550 window. But at that point, your dispersion is not zero, which is something around 17 picosecond per nanometer per kilometer. So this is one of the limitations of the conventional optical fiber, that you have to send a signal at a wavelength with at which the loss is minimum, but dispersion is not zero. Now, the second point, send a signal, and you want that communication should be a single mode communication, because there are certain applications in which you can have the multi-mode signal, but there are certain applications in which you must need to send a signal which is showing the single mode operation. And for example, if you want to send a signal for long haul communication, right, and you want to avoid the dispersion, your you have to use a fiber which is a strictly single mode fiber. uh, so this is one of the application. The second one, if you want to use your fiber to be designed for a high power fiber laser, in that case also, in order to avoid the overlapping between the modes, and in order to maintain the good quality of beam quality of your laser, you have to use a fiber which is a single mode fiber. And the moment you are discussing about the single mode fiber, it is giving you a limitation, and that limitation is your core size. Roughly we can say the core size should be less than 10 micron, right? So this is again giving you a limitation on the power handling capacity of your fiber. The another point, which you can see here, the low birefringence. If you talk about a optical fiber which is completely symmetrical in shape, so the different polarization, if you talk about X and Y polarization, the X and Y orthogonal polarization will actually see the similar refractive index profile because it is completely symmetrical design, right? It is a completely symmetrical design. So both the polarization X and Y orthogonal polarization will see the same refractive index. So the propagation, the constant beta will be same for both. So the velocity will be same. So if you try to see what is the birefringence, which is the difference between the effective index of the X and Y polarization, that will be very close to each other, right? So the difference of the X and Y polarization effective index will be order of 10 raised to power minus 8. So this, suppose if you want to use an optical fiber where we want to create the mode filtering, where you want to create the mode filtering based on the polarizations, you want to keep only one polarization, right? So that is really difficult in this kind of the conventional optical fiber. And that is why you will see in the some of the designs they are talking about the highly birefringent fiber, means you want to keep this term as low as possible, maybe something order of 0.001 only. So if you talk about the conventional fiber, no, you cannot give, your birefringence will be very small. Now, the another point which I talked about the optical fiber is, that when you send the signal through an optical fiber, your aim is to, receive this signal with less loss at the at the output in. There are two factors which basically degrade the quality of this signal at the output in. One is the dispersion we have just discussed about, and the second one is the loss, right? We can minimize the loss, but if you're sending a signal through silica or fiber which is made up of silica, then it is having certain loss, and because of that loss, the whatever the power of the signal you are sending, that is going to decrease. And in order to get the uh, in order to receive the the signal, what you do, you try to use the amplifier, right? This is the way to use it, amplifier. So in optics, what amplifier we have? Optical communication, uh, we use a optical amplifier which is called EDFA, or DRDO fiber amplifier. So in in the second part of my discussion, we'll see the EDFA basically gives you the uneven gain. It is not giving you same gain for all the signals. You are using an optical fiber not to send only one channel. You want to send the information to the different channel, so that more and more information you can send at the same time. So if you are sending one signal at 1550 and the another signal is the nearby wavelength, and both the signal when will propagate from one place to another place, there will be a loss in the signal. But when you are going to use the amplifier, that amplifier is not going to give you the same gain for these two nearby wavelengths. So what will happen if you pass these the wavelength through the EDFA, which is not giving you the same gain for all these signals, your amplified output signal will not going to have the same power level. So this is one of the limitation of the conventional EDFA. So in order to address this, again, we have to look for some spatial design. So this is the point why we are looking for the spatial design. Few points I've just mentioned over here. Now the question is how we can, what do you mean by the spatiality optical fiber? So the answer is basically fiber design that breaks the limits set by the conventional optical fiber. Just we have few of them we have just mentioned is known as the spatiality optical fiber. Now, how to achieve this spatiality optical fiber? If you just see all the designs, all the spatial designs, which comes under the category of the spatial design, spatiality optical fiber, mostly it is achieved by tailoring the refractive index profile of the fiber. Because in case of fiber, what do you have? You have the refractive index of the core, refractive index of the cladding, and their width. So by tailoring this profile, you can come up with some new design. So here I have shown you only two designs specifically, uh, which comes under the category of the spatiality optical fiber. In the first one is called double clad W fiber. It is shape is W kind of shape, so it is called W fiber. Here you see, it is not only you have one core and then one cladding. You have one core, then you have low index cladding, and then you have another cladding, right? And the shape of this is controlled by two uh, design parameters, delta 1 and delta 2, and then you have A1 and A2. So here, this is what we have done. You have given a new W type of profile, which is by tailoring the refractive index profile in the radial direction. Now, the second example which I have taken here, you can see the refractive index is basically tailored not in the radial direction. Basically, it is tailored in the angular direction. It is basically tailored in the angular direction, and that is why I have taken this example. This is the example in which you have tailored the refractive index in the radial direction, and it is azimuthally in the angular direction. If you'll see, there is no change in the refractive index profile. But this is the case of the spatiality optical fiber, where you can periodically see there is change in the refractive index. If you move in the cladding region, you have low index, high index, you have high index, low index, high index, low index, high index, and low index region. And this periodicity is basically controlled by the angle theta1 and theta2. So this is called the spatiality optical fiber. Now, during my lecture, I will basically try to touch upon the spatial designs. Three spatial designs. One is spatial design for the large mode area designs, which is basically used to design a fiber which can be used as a host material in order to achieve the high power laser. The second one is the dispersion compensating fiber, and the third one is the gain flattened optical fiber. So my first stress will be on the designing the optical fibers and waveguides, not only the fiber but the waveguides, which can be used for the high power laser application. And for the rest part of my discussion, briefly I will address about these two designs. One is the dispersion compensation, and the second one is the gain flattening. These two are basically addressed if you want to have the better signal output at the output end. So I'll start my discussion with the designing of the large mode area fiber designs. So I'm going to talk about this. Now, the before I'll go to this large mode area designs, I will have already mentioned that why we are looking for the large mode area fiber designs, and what do you really mean by it. So large mode area fiber designs are a design which can give you single mode operation with a large mode area, and this design is basically useful if you want to achieve a power level by a optical fiber more than the level which is set by the conventional optical fiber, right? So we have to look for the laser. So since we have to talk about the lasers, I will start with this very interesting phenomena, which is called the light matter interaction. Because you'll see what is laser. Laser is nothing but it is basically the one of the output of the light matter interaction. And in physics, you know that the condition is very important. You know, the light is going to interact with the matter. What output you will get, that is going to depend on the conditions. So here I have drawn one schematic diagram. You know, when light is going to interact with the matter, and if you increase the energy level of the light, you can see the different effects which you have seen in your BTech first year physics. uh, in one case you will see the effect which is called the photoelectric effect. If you further increase the light, means energy of the light, you can see the Compton effect, and finally you can see the pair production. So these are the three different effects which comes from the light matter interaction, and I hope that everybody is aware about this. Now, if you talk about again the interaction of the light with the matter under a spatial condition, which is called the stimulated emission, then we get a light. Then we, as a result, we get a light with some unique feature, and that light is called laser light. And this idea was given by 1916, way back in 1916, by Albert Einstein, that if you interact the light with the matter, you can get the light with some amplified light, uh, with some special feature which are quite unusual, because we know that when the light passes through any matter, the in the output sections, whatever the light you will get, that light intensity will be small, and because of the number of the losses uh, included in the interaction. But the idea was given that if there is a possibility of spatial condition which is called stimulated emission, then you can get a spatial light, and that light is called laser light. Now if you talk this spatial light is also a light having a spatial feature. And if you talk about this light interaction with the matter, again you can get some unique phenomena which comes under the category of the nonlinear optics, because this gives you the possibility to have a very intense light, which is not there in this in the previous case. So what you can do here, you can pass a particular wavelength lambda 1 and lambda 2, and the output you can get the light which is lambda 1, lambda 2, lambda 1 plus minus lambda 2, and so on, which is not there in the case of the linear effect. Similarly, we have the other effects also. Super continuum generation means you send a light, you send an intense beam, and that intense beam is going to interact with the matter, and in the output you are going to get all the different colors, right? So this is called super continuum generation. So this all is coming because of the condition, spatial condition. So laser is a very important light, and this laser light has changed and opened basically the new fields of uh, fields which is called nonlinear interaction field. Now, uh, this point I have already mentioned. What is this stimulated emission and spontaneous emission? That you already know. If there is intense incident radiation, and that incident radiation stimulate any stimulate the emission of the photon from excited state to lower state, that particular radiation is basically called the stimulated emission. In case of the spontaneous emission, you get the photon. In case of stimulated emission, you also get the photon. But the difference between the photon which you get from the spontaneous emission and stimulated emission is, in case of the stimulated emission, the emitted photon and in this incident photon will be in the same phase. And this is the reason for this is the reason for your laser action. But at the same time, I will like to mention specifically that this spontaneous emission is very essential, because this emitted photon only going to trigger and start your laser action. So if you don't have any spontaneous emission emitted photon, you cannot have the laser action. Now, what are the main components of the laser? The main components of the laser are resonator, gain medium, and pumping. So laser is what? We have seen the name of the laser is light amplification by stimulated emission of radiation. It is amplification is written over here, but laser is not an amplifier. Essentially, the laser is an oscillator. Laser is basically in the oscillator, and this oscillation process is achieved by using the resonator. So I want to mention this point specifically, that you should know and you should always recall, this is not an amplifier, this is basically the oscillator. So we will discuss about the development of the laser. The first laser, the idea was given in 1916, but the first laser was invented in 1960, which was the ruby laser, and then it was basically a pulse laser, and that was the major breakthrough in the field of photonics to look for the possibility to um, come up with some new lasers having by using the various gain medium like solid, gas, and liquid, and try to find out the laser output with some uh, in by the increased power level or different power level which can be used for different applications. So this is the uh, one of the chart which I have summarized here. You can see the different medium and different type of laser which is already there in the field. So I'm not going to stress upon these particular lasers, but you can see you have different medium laser has been used, and their output wavelength is also different, and their applications they are used depending on the power level, and depending on the power level, output power level, and their operating wavelength, they are used in the different field. They are basically used in the different field. Now, if you talk about these lasers, one of the problem with these lasers is the thermal management and their size. They are basically bulky in the size, and if you want to use a high power laser, these particular lasers, for industrial application, that is fine. But if you want to look to have the high power, which can be used, which can be very handy, and you can take that particular laser from one place to another, that creates a problem, because the power level, if you want to design a particular fiber like specifically the carbon dioxide laser, and you want to use it for the high power, something around 1 kilowatt, the size is really, is a really big setup, and it cannot be moved from one place to another. So if you want to use the kilowatt laser, which can be transferable, easily transferable from one place to another, then that is the problem. So the question comes, why we are looking for the fiber laser? The answer I have already discussed about you want to design a particular uh, laser which can be easily handled, moved from one place to another, and can be used for the so if this kind of laser is there, which is not very bulky, and still it is giving the comparable the output level, that can be have various applications. The another advantage of this using the fiber laser is it's having very with, good thermal optical property, which can it's basically a very good heat dissipator due to its large surface to active volume ratio. So whatever the problem is there thermal, that is basically inherently controlled by the fiber. So, if you conclude why we are looking for the optical fiber laser, one is the light weight and small in size, easy to handle and carry at different place and locations. And because of this, there, one of the biggest advantage of our application of using these laser is in the defense and industry. And at this point of time, I will like to address this point, because few years before I was in that particular team, uh, where so I was in the evaluation team, and in the DRDO. So there, the aim of the DRDO is to come up with the indigenous technology to develop the high power fiber lasers. Earlier, they have done it with the help of the Israel team, and now they are trying to, and at some extent, they have done it also, because having a major application in the defense. So they are looking for the technology to develop the uh, the high power fiber lasers for the applications in the defense. So this basically point out the the importance of the topic of fiber lasers. So this is the typical refractive index of any fiber or waveguide, and where this is the refractive index of core and cladding, and this is the width of the film, you can say. Now, depending on the difference of N1 and N2 and the width, this waveguide gives you the provides you the number of modes, right? If you're looking for a single mode operation, so single mode operation means this N1 minus N2 should be small, and this A should be also small, right? So for any fiber laser, your supporting waveguide or fiber should be only single mode. Why it should be single mode? Because if it is a single mode, its beam quality is going to be very clean. But if you are going to use a fiber or waveguide as a host material, where you want to dope it the core region with the erbium or other the rare earth material, thulium, and then you want to use it for waveguide laser, since its design is such that it is going to support more than one mode, so all the modes will propagate, and at the output end you'll get something, the overlap of all these modes, and the beam quality is not as good as of in case of the single mode fiber. It is not that you cannot design a high power fiber laser with by using a multi-mode fiber. You can do it, but if you want to look for a fiber laser where you don't want to compromise with the beam quality, then you have to go for a single mode fiber, single mode, single mode fiber or waveguide. Now, when you're talking about the single mode fiber or planar waveguide, the condition is that you can achieve this with a only small core. Basically, your core radius should be something in 5 to 10 micron, depending on what wavelength, operating wavelength you're talking about. But this is the condition that V value should be less than some cutoff value, 2.4048 in case of optical fiber. So in other words, if you want to design a single mode fiber, your core area should be small. And if the core area is small, it means it is basically going to give you very tight confinement, to the light which is propagating to the core region, and basically it reduce the optical damage threshold of the waveguide. It means you cannot launch a power beyond a limit. So that is actually giving you one of the limitation on the output of the fiber laser, and at the same time it can also give you some the nonlinear effects which is not required in this particular operations. So the question is how we can increase the power level, because you want to increase the power level, but the problem is when we are going for the multi-mode, the beam quality is reducing, and if you are talking about a small core, there is a limit on the power handling. So the answer is yes, you can do it, but the only solution is you can do it if and only if you come up with some design which can give you the single mode operation with a very large core area. These designs are basically known as large mode area designs. If you go to the literature, you'll find out, the series of designs are there, because this is the progress of the structure. So mainly if you categorize these LMA designs, so one of the way to achieve this LMA design is by controlling the index difference between core and cladding. Means what you can do, you decrease this n1 minus n1 minus n2 value. Okay, you decrease this n1 minus n2 value and increase the a value. So with the help of that, you can increase the a value. But the problem is there is a uh, there is a problem in the fabrication. It's very difficult to control the index difference between the core and cladding. And the second point is, if you reduce this n1 minus n2, more and more field will go into the cladding region, and your fiber or fiber layer which you are designing, that is going to be more sensitive to the bending. So, but of course, this is there has been the designs based on which you can further increase this and break the limits of the conventional fiber. The second way is you tailor the refractive index profile inside the core. So inside the core, you don't take the the step index design, but you, instead of that, you take the some Gaussian kind of design, and you can basically increase the area. But in that particular case, the modal field pattern deviates from the Gaussian. So this is one of the limitation. So the another way which I can classify by the use of the photonic crystal fiber, we'll discuss about this photonic crystal fiber also in the coming PVDs. So what we are actually working on, we are basically working on a fiber which is LMA fiber, which is called leaky fiber. So what this leaky fiber tells about, so we have number of designs we have already given, and all are basically based on the principle. So I will try to focus on the principle which is there. So what we do in this kind leaky designs, we increase what you have. You have a core and then you have a cladding. You have a core and then you have a cladding. So what you can do with here. So if you want to use a large mode area, means your core radius should be large. So we are saying that, okay, you take a large core so that it supports number of modes, and then you tailor the cladding. You don't take the step index cladding, but tailor the cladding in such a way, that it gives, the loss to all the modes. It gives the loss to all the modes, keeping in mind that the loss for the fundamental mode should be very small and the loss for the other modes should be large. So if you can do it, then what will happen? You are launching the light here, and initially you have a multi-mode propagation. As the modes will propagate inside the fiber, after few meter distance, all the higher order modes will be filtered out, and you are left with a single mode fundamental mode, and that fundamental mode is propagating through a large core. So this is the main principle. So the that's why I have mentioned here, this basically works on the principle of mode filtering. Mode filtering means you take a large core, launch the light, it will give you the number of modes. Now the tailor, your cladding should be not a step index cladding, not usual conventional step index cladding, but the cladding should be such that it should give you loss to all the modes, and by maintaining the condition that the loss should be minimum to the fundamental. So that being a designer, this point you have to make sure that you are tailoring the cladding, but while tailoring the cladding, you have to ensure that the loss of the fundamental mode should be minimum. All right. So this design we are talking about. So if you want to talk about our leaky designs, you should know what do you mean by the leakage loss. So in order to explain that, I'm just giving you the idea about the ray theory. When you talk about the ray theory, you say that by the multiple reflection, by process of total internal reflection, the light is guided from one place to another. The another approach and the better approach is to understand the propagation of the light through an optical fiber is not the ray theory, but it is basically the wave theory, and which is called the modal analysis. So you have this kind of refractive index, and when you launch the light, it basically gives you the various modes. And these, what are these modes? These modes are basically a particular intensity pattern which propagates through the optical waveguide without changing its shape. And these modes are basically characterized by the propagation constant or effective index. And this you can easily relate if you have already done a problem which is called the particle in box problem. There also you have a similar pattern. You have a particle in an inverted box, and when you solve it, you solve the Schrodinger equation there, and then you get these definite solutions. So similarly here also we have a refractive index profile, and we are the light is bound to propagate through it, so it is giving a definite solution. And in physics, you know that whenever you apply certain conditions, you come up with the discrete solution, right? Here also the light is bound to propagate through in this optical fiber, so it is giving you some discrete solutions. And these discrete solutions are called the modes. So this is the modal analysis. You have the waveguide or fiber, and this is the second order differential equation when you put the conditions. So this is typical refractive index profile, and I mentioned that you will find out some discrete solution. These discrete solutions are called modes, and they are basically characterized by the electric field. This is the electric field, a particular electric field of the fundamental mode. So you can see in the high index medium, your solution is basically the oscillatory solutions. However, in the low index medium, which is the cladding, you have the exponentially decaying solutions. So this is called a guided mode. So in a guided mode, when we have this kind of refractive index profile, in the core region or high index region, you get the oscillatory solutions. And in the cladding regions, your fields keep on decreasing exponentially. Now, see, in this particular case, your most of the field is there in the core, but there are certain field is there inside the cladding, and it is keep on decreasing. If you introduce in the cladding region this kind of high index region, then whatever the power is here, if after this region, it will not continuously decay out, because in this particular region, your refractive index is again a high index. So you'll get a oscillatory solution. So whatever the power is there will keep on oscillating. And what you will see that this mode is not a guided mode. This is a leaky mode, because power is leaking from core to cladding. So in all of our design, wherever we are talking about the leaky modes, we will talk about this structure where the high index region is having the refractive index, which is there equivalent is equal to the core index region. So this is a particular leaky structure where we have a large core leaky structure, and we have number of modes. This is the fundamental mode, and these are the higher order modes. So depending on N1 and N2 and D, we have number of modes here. Now, if you take a refractive index profile, something like this, in that case, these two modes will become leaky, because their value is smaller than this higher index region refractive index. Now, if you change the refractive index profile something like this, all these modes will be lossy modes or leaky modes. But if you take this kind of structure, then all the modes will be leaky modes. The loss of these modes, the leakage loss of this mode is basically going to depend on the propagation constant and the distance of the high index. Means what is the propagation constant which is there in the high index medium, and important point is it is going to depend on the distance up to which this particular distance after which the high index region is going to be appear. So the larger will be the gap, smaller will be the loss. So a better way is to give this kind of structure instead of the previous one, because in the previous structure, all the modes are looking at the high index region at the same distance. So it will be better. What is your aim? Your aim is that your loss for this fundamental mode, the first one, should be minimum and it should be greater for this. So instead of giving this kind of profile, if you give this kind of profile, then the fundamental mode which you want to have it here will see the high index region at a larger distance in comparison to the all unwanted high index modes, and this will increase a loss ratio between the fundamental mode and high order mode. So this kind of structure is one of the given structure for leaky designs. So I will start with the planar structure. This is one of the planar structure we have proposed for the waveguide, not for the fiber. This is 1D waveguide, where the waveguide is basically characterized by the uniform substrate NS, and uniform core, which is characterized by a width of A and refractive index NF. Then we have tailored the refractive index profile of the cladding, which is controlled by a power law profile, which is given over here, and power line profile looks like this. So initially we will going to take a large value of A, so it will support number of modes, and as these modes will propagate, we'll get the effective single mode operation by the process of mode filtering. Which method we have used to calculate the loss here? Briefly, I'll mention that we have used the transfer matrix method, in which this particular region is divided into n number of regions. So we have a graded index profile. So this graded index profile is divided into n number of the step index profile. And then field has been written in all the layers, and by using the boundary conditions, what are the boundary conditions? One of the condition is in the high index region you have a oscillatory solution, which is sine and cosine, and in the low index region we have decaying solution, which is cos hyperbolic and sine hyperbolic solutions. So by using this condition in each layer, we have find out basically the layer which is giving you the relation between the coefficients of the two consecutive layers. I'm not going into detail of this, but if you solve it, you'll basically, and you use the finally boundary condition that in the leaky cladding only outgoing waves are allowed, and in the substrate region where there is no high index region, the field should die out. By using these conditions, we basically find out the beta value, and that beta value is giving you the loss as well as the real part of the beta value is giving you the effective index, and the the imaginary part is giving you the leakage loss. Here we have used some normalized parameter A, B, and V to analyze the results. So as mentioned, this is beta is basically your complex number. So if you put it there, you'll find out the real part of it and imaginary part of it. So first we have once you are giving any particular design, you should basically go to study all the parameters very carefully on these designs, so that any person which is going to fabricate it should be aware about the design parameters and its effect on the operation of the design, whatever you have given. So first we have seen the effect of profile parameter on the BR. Means this is going to talk about the effective index. So you can see the linear property is not going to be changed by this Q profile, this Q value 2 or 3, 4, 5, whatever you have taken, it is almost constant. And the second point, you can easily see that the effective index of the fundamental mode is greater than that of the first higher order mode, which is quite obvious. the very important point is about the effect of the leakage loss. This BI is somehow giving you the information about the leakage loss. So we have seen, is this Q profile is going to control the leakage loss of the structure. So it has been calculated for the 3 different values of normalized frequency parameters 6, 8, and 10. If you focus on one particular figure here, you can see as you increase the Q value, means profile parameter, the loss is increasing. Loss of both the modes are increasing continuously. And this is because as you increase the Q value, your leaky structure comes closer to the your core regions. I have already shown in the first diagram for different values of Q. There you can see, if you increase the value of Q, your leaky structure will come close to the core region, and that's why the loss of each mode will increase. The second point, and very important point, which you can note it down here, for any given value of Q, either you take Q is equal to 2 or you take Q is equal to 5, you can see the loss of the first higher order mode is greater than that of a fundamental mode. So if you want that this mode should be come out of this structure, you have to increase this loss and you have to minimize this loss. The third point, which you can see, by changing the V value, the absolute loss is increasing. So absolute loss is increasing, and this effect we should know, because at some point of time, if you have some value of the leakage loss and we want to increase the absolute loss, then we should know what is the effect of parameter. So here you can see, by increasing the V value, the absolute loss is decreasing. Why? Because as we increase this V value, more and more power is basically confined inside the core region, and less field is going into the leaky cladding region. So we can see here, by controlling the V value, we can control the absolute loss. Similarly, we have also seen the effect of B by A parameters, and this is also giving you information that if you change the B by A means the width of this leaky cladding, right? Then the loss is decreasing, but at the same time, the differential leakage loss is also increasing. So if you want to increase the differential leakage loss, the outcome from this analysis, you can get it here. See, here the differential loss is this one, and here the differential loss is huge. So if you want to increase the differential loss, you should basically play with this B by A parameter. So here some typical results we are talking about. So for these given design parameters, the loss of the fundamental mode is coming around something around 0.2 dB per mm, and first mode is coming something close to 5 dB per mm. So the idea is, if you have a waveguide of this design, a 5 millimeter propagation distance can filter out all the unwanted modes, and you can get the single mode propagation, which is almost 2.25 times larger than that of conventional waveguide. So bending analysis is also very important for this. So I'm not going to detail into this, but we have because we have to cover the other topics as well. So, but I'm just showing you one result. You can see that we have done the bending analysis, and it is showing that it is insensitive to the bending radius larger than 3 centimeters. So this design which we have given, it is having good bending sensitivity. That design we have given is a graded kind of structure, but it's not easy to design a graded kind of structure. So in order to give a simplest design, we have given only the simplified design structure, and with this simplified design structure, this structure is again able to show this single mode operation. So the conclusion is the leaky designs can basically use to design large to achieve large mode area operations. So this kind of waveguide structure can be used as a host waveguide. This can be, this directly cannot be going to use as a fiber laser. If you want to design a fiber laser, you need to dope the core with the rare earth um, medium, but this can be used as a host to design a waveguide laser or fiber laser. The second one is, we have talked about the multi-clad leaky optical planar waveguide. And this has given, while doing this analysis, has given some new effects. And with the help of new effects, we have come up with some new designs as well. So this is one of the refractive index profile of the planar structure. Instead of having only the change in the refractive index, what we have done, we have substrate here, then we have a uniform guiding film, and in case of the leaky cladding, earlier you have seen we have changed the refractive index like this, but here we are not changing the refractive index like this, but instead of this we are using the low and high index cladding, where we have tailored the index of low index cladding by this Q profile. Okay, so the high index region is having a width of d minus pitch. So this is your pitch value. Pitch value means after which this there is a periodicity of high index, low index region in the cladding region. So you can see here in the cladding region, what we have low index region. This is low index region. This is low index region. This is low index region, as well as we have high index region. This is high index region, and this is high index region. So all the high index region is having the same refractive index as that of the guiding film, but the refractive index of the low index region is tailored by using this particular profile. So because in principle it is easy to design a stepped index kind of design in comparison to the graded structure. So once we have done it, we have seen the effect of Q, because you need to see what is the effect of this Q profile. So once we have done the effect of Q profile, you see, if you just look at the loss of the fundamental mode, it is increasing and finally settle down. If you just look at the loss of the first higher order mode, it is increasing, then it is showing you some peak, and then it is coming down. This was a quite unusual thing for us in the beginning, because expected was your loss should be increased. Those loss should be increased with the profile parameter, but here we got one peak and then it is coming down. And then if you look at the next higher order mode, it is increasing, it is not showing any peak, but there is some region, peak region, where you can see the loss of the first higher order mode, even it is more than the next higher order mode. So this was not very conventional thing which we came across. If you change the material, then there is a possibility that you will get the usual design, but we'll stick to this and we'll try to find out why this particular thing is coming about. Because if this is there is no problem in that, and you have done right calculation, and this is because of any effect, then this is really good, because this is increasing the loss between the fundamental and higher order mode. So we have done this analysis and we have find out that this is because of a effect which is called resonant coupling between the first higher order mode and the leaking and the cladding, right? So from this we have chosen the operating range for the single mode operation, and we'll find out the single mode operation is there in between 0.5 to 2 micron. Specifically, if you take Q is equal to 1, because of this resonant coupling, which is somewhere here, the loss of the loss of the first higher order mode and second higher order mode is almost same over here. So in the absence of the resonant coupling, maybe your fundamental mode, your first higher order mode is coming somewhere here. So the difference of the loss has been increased because of the resonant coupling. For example, you can see the loss of the fundamental mode is coming 0.13. However, the first and next higher order mode is coming close to 10 dB. Means if you take this design parameter Q is equal to 1, You can achieve a single mode operation just with a 2 mm long propagation length and with a core size which is approximately 3 times that of your conventional structure. So as a conclusion, we saw that there is a special effect which is called resonant effect, which has increased the differential leakage loss in the structure. Then we have seen the effect of this B by B lambda parameter, and with this B by lambda parameters, you can see there is a ripple in the first higher order mode loss. So this ripple is also the confirmation of the uh, resonance coupling which we have observed. And the second point you can see with the effect of B by lambda, we are basically increasing the differential leakage loss. So being a experimentalist, you have to see how many dip or how many low index region you can design, and based on that you can you can basically use the D by pitch value. Then we have seen the effect of the effect of this D parameters as well, because we need to study each and every parameter here, and we have concluded that if you increase this for a given value of D by pitch, increases in capital lambda will basically going to decrease the loss. So these studies, whatever we have done, are basically used to optimize the parameter for the experimentalist when he is going to fabricate any such designs. This is the particular modal field. We have drawn it for the fundamental mode and the first higher order mode. You can see clear, this is the substrate region. So in the substrate region, the field is almost zero here. However, in the core region, field is there, and in this cladding region, leaky cladding region, you can see there is a oscillation in the field. This is a signature of leakage loss. And one more thing you can see, the oscillation is there in the both the field fundamental and the first higher order mode. The oscillation in the first higher order mode is much larger than that of the fundamental. This is the contour plot, we have shown it here, and this contour plot is giving you that most of the field or the fundamental mode is confined inside the core region. Again, the bending loss analysis we have already done here, so I'm not going into detail of this. Yes, again, once again, since it comes across the resonant coupling, so in order to give a simplest design, what we have done, we have not taken so many low and high index region. We have just taken 2 low index region here and 1 high index region in the cladding. And by tailoring the refractive index, by just tailoring the refractive index of this N3, which is the low index region in the cladding, we have tried to tune the coupling of this first higher order mode with the with the fundamental mode of this outer region, and we have done it, and we will find out there is a resonance coupling for the N3 is equal to 1.455 for the N1 and N2, these given values, with the A is equal to 10, and with this parameter what we have, we have the loss of the fundamental mode and the first higher order mode is coming close to the 20 dB. So without using the complicated structure, but it comes from there only. When we have created a complicated structure, we have tuned the profile Q, and because of that we came to know about this thing, and that has further simplified the structure, and we are able to get the single mode operation with this simplified design with only 1 mm propagation distance. We have also seen the bending loss as well as the spectral variation of this, and what you can conclude it from here, from the spectral variation of this given structure, that it is not just giving you single mode operation at one given 1.55 or 1.3 wavelength, but you can get the single mode operation in the range of 1.15 to 1.16 propagation length. Only thing is basically you have to see the length of the waveguide which you can give you the single mode operation, but this is giving you the single mode operation in a range of wave. So one of the outcome which we'll get it from here is basically we got to know about a resonant coupling effect, and this has opened a new door for the other application. In the later part, when I'll discuss about not about the fiber, but I'll discuss about the grain flattening and dispersion compensation, where I will show you this particular effect we have utilized for mm, for these applications. So we have we talk about the 1D, we'll talk about the 2D structure. So 2D structure, I will not go into details, much detail, but I'm just telling you, we have given the structure design for the 2D structure, and we have analyzed by using the effective index method, in which we'll first solve the structure in one direction, and then we'll come for the effective index profile, which is solved in the other directions. And we have shown the results, and results are clearly again giving you the information that you can get the single mode structure. And the second important point is about the structures is it is giving you, you know, the extended single mode operation. Extended single mode operations means it is giving you not a single mode operation a particular wavelength, but in a range of wavelength. Like for channel waveguide, it is giving you 750 to 600 nanometer single mode operation. Why? Because at 1600 nanometer, the maximum loss which is there is 0.4 dB, and at 750 nanometer, the minimum loss of the first order mode is coming something around to 4 dB. So you can ensure a single mode operation in the range of 750 to 1600 nanometer wavelength range. This is a modal field profile. You can see clearly that leaky modes. This is a first order mode where the loss is more than that of fundamental mode. This is well confined fundamental mode. You can see for a typical results, you can get a loss of close to 16 dB for the first higher order mode, and for the fundamental mode is again low loss. So with a propagation distance of close to 1.2, you can get a single mode operation. Again, we have given a simplified structure, and this simplified structure in the channel waveguide is also ensuring the single mode operation. Now I'm coming to the fiber. So I will skip this because we have so many things to cover, and I think approximately 45 minutes time is remaining. So I'll come back to the fiber, leaky fiber designs. So leaky fiber designs is having a core. It is the angularly symmetrical fiber in which we have a constant uniform core, the core having constant refractive index. And again, we have a multi-trench fiber where we have a low and high index region, and the refractive index of the low index region is tailored by this Q profile. Okay, just we have seen in case of the waveguide. So if you analyze the effect of Q profile, you can see here the loss of the fundamental mode and the loss of the higher order mode. The difference is of almost 1000 times, 3 order of magnitude. So 3 order of magnitude is there. All right. This is, and the second point is always the loss of the fundamental mode is greater than that of the loss of the first order mode is greater than that of your fundamental mode. Then we have seen the effect of B by pitch parameter. Again, B by pitch parameter is as we have seen in case of the planar waveguide. Again, the P by pitch parameter is not just decreasing the leakage loss, but at the same time, it is increasing the differential leakage loss. So being a designer, you have to see what kind of design you want to give it for the fiber. If you want to, or you want to just decrease the loss, or you want to decrease the loss, but at the same time you want to increase the differential leakage loss with the ratio of the first higher order mode and the other one. So accordingly, these parameters you can choose for design. Next, we have shown the effect of the D by pitch value, and the major conclusion which you can get it from here is that leakage loss decreases with the increase in the duty cycle for a given pitch. This and the leakage loss increases with the pitch value. So this we have pitch value. If you increase the pitch value, the leakage loss will increase, but if you change this D value, this is going to decrease. So all these effects are basically to come up with certain design within the limitation of your fabrication. So next we have seen the effect of numerical aperture. So as it was quite obvious, if you increase the numerical aperture, means light is more confined inside the core, the loss will decrease. So same pattern we have get it from here, but the only difference is that now in this case loss will decrease, but the differential leakage loss will almost remain same. So now you have to see you want to just decrease the loss while maintaining the differential leakage loss, or you want to decrease the loss by increasing the differential leakage loss. Accordingly, that parameter you should change. Next, we have seen the spectral variation of this design, and this design is also giving you single mode operation in the range of 1.45 to 1.7 micrometer. I have just shown how to choose the range, operating range, just in the last few slides before. Again, you see the fundamental mode, which is well confined inside the core. This is the contour plot of this same. So as a conclusion, we got that you can get it with you can come up with some design in the fiber which can give you the single mode operation with a large core area, something close to 700 micrometer square, and this kind of designs can be good candidate for high power laser application. Now in order to see whether the design is there, verification of the results with the experiment, we have proposed a simple structure. This is simple structure, when this calculation tells that this simple structure will give the loss to the first higher order mode, which is close to 8 dB. So the calculation tells that you'll get the 20 dB loss in almost 3 meter propagation distance. So in approximately, if you fabricate a fiber having this kind of refractive index profile, that will give you the single mode operation after 3 meter propagation distance. So the fiber was fabricated by one of our collaborator in University of Nice, France, and they have fabricated this design. This is the refractive index profile of the fabricated design, and this was the design which was given. So when we have done the analysis, they have fabricated this design. They have fabricated this particular design fiber, and they have launched the light from one end and seen the output of the light for the different propagation length. So they have taken the different length of the fiber which is fabricated here, and you have tried to see the output. So this is the picture which is captured of the output of after 1 meter propagation distance. So now you can see here that the output is not very good. It is basically the overlap of number of modes. Then if you look at the output after 2 meter propagation distance, you can see some of the modes has been filtered out and just some better quality than the previous one. And after 3 meter propagation distance, they have also observed the only single mode propagation. So this was the experimental verification of the principle which we were discussing till now. And we have also compared the field profile, experimental field profile, and the measured field profile, which is giving you the good agreement. We have also measured the the loss in the range of the wavelength, not only at a particular wavelength. So it was measured from 1.51 to 1.56, and you can see it from here. There is a good agreement. There is a good agreement in the loss which has been experimentally calculated and done by the simulation. So this has given the idea that whatever the we have proposed is not just in the theory, it is there in the experiment. So this is the conclusion, that basically we come up with one design which has given the single mode operation with a core something the order of 25 micron and mode area close to 700 micrometer. And this design, the working of this design has been verified with the experimental results. Now, the next point which we have discussed there is the resonant coupling. By using the resonant coupling, we have simplified the structure and we have come up with a design which is called dual core fiber design. So resonant coupling design has been used in fiber for the large mode area. In the coming section, we'll see that this resonant coupling structure has been used for the two more applications, which is the dispersion compensation and the gain flattening. So that I will discuss in the brief. So what we have done in dual core fiber design, so being inspired from the what we have observed there, we have given a simplified design which is having uniform core and a leaky cladding. So uniform core is characterized by a radius A, core radius A, and refractive index N1. And leaky cladding is what? Leaky cladding is having the low index region and high index region. Okay, so the low index region, we have not number of low index region, we have two low index region. One is the inner cladding, which is characterized by refractive index of N2 and width D1, and then we have an outer cladding. We have an outer cladding which is characterized by the refractive index N3 and width D3. And high index region is having the same refractive index as that of core, which is N1, and width is D2. Now the first job is basically to find out the value of N3, such that the effective index of the fundamental mode of this inner core should match with the fundamental mode of the outer core. So that can be done by tuning this N3 value, because when you tune the N3 value means we change this value, low index region from here and go upward, the structure will change and the effective index value, this is going to change. So basically N3 tuning will be key to find out the resonance coupling conditions. And when the resonance coupling starts, there is a transfer of, you can see the quick transfer of the power from core to cladding. So in order to do that, what we have done, as we have mentioned here, we have tuned the value of N3 from 1.436 to 1.444 value. And you can see when we have changed the value of N3, initially the loss of the fundamental mode is smallest. Then we have the LP11 and then we have LP02. Quite obvious trend we get it here. But when we have increased the value of N3, we'll actually reach to a position where the loss of the fundamental mode cross the loss of the next higher order mode, and it is going beyond to this, and finally we'll got a peak of this, and this peak is basically giving you the resonance coupling condition. So this N3 has been used to tune the effect of resonance coupling, and because of this we'll get the better differential leakage loss. At the same time, if you just look at the effective index of these modes, this is unaffected by the N3 parameter. So we have fixed the value of N3 parameter, which is there 1.4425, and then we have tried to see the effect of other parameters, which is the D1, D2, and D3, whatever the parameters we have talked about. So you can see when you increase the D1 value, the loss of all the modes keeps on decreasing, because D1 increasing means you are going away from the core region. So loss will obviously is going to decrease. The another take out from this particular analysis is, if you want to decrease the you want to decrease the absolute leakage loss of all the modes without changing their differential leakage loss, then you should basically change or play with this D1 parameter, because the D1 parameter is going to increase or decrease the loss of the individual modes without changing the differential leakage. Then we have seen the effect of D3 parameters, and D3 has again given you, the crossing of the loss of the fundamental mode. So we have two crossings here. One crossing is here and one crossing is here. If you try to find out these crossing points carefully, you can see that, at this particular crossing point, uh, the loss of the fundamental mode is very small. So you may think that we should choose this particular one, value of D3, but it is not just the loss of the fundamental mode. You have to also see the loss of the higher order mode, right? So in case of this particular thing, the loss of the fundamental mode is something around 0.01, and LP11 mode is 55 dB per mm. So this can give you the single mode operation with a very small length of fiber, which is 36 centimeter length of fiber, very small length of fiber. All right. However, if you just look at this particular crossing point, this particular crossing point will give you the loss of the first higher order mode, which is much greater than that of the your in this particular case. Here you have 55, but here you have close to 200, 186. So this can give you single mode operation in a very small length of fiber. But the problem is in this particular design parameter, the loss of the fundamental mode is also not bearable. All right, so that's why we need to go away from this design parameter. So better one is this one. Then we have seen the the spectral variation of the leakage loss, and in the spectral variation of the leakage loss, you can also see the crossing of the leakage loss curve of the fundamental of the first higher order mode and LP02 mode. So this is the another confirmation of the resonance effect. This is the field profile. You can see the field profile fundamental mode, this one with the solid line is well confined, right? And in the other modes, you can see oscillation, huge oscillation, which is the signature of the higher loss. Fundamental mode contour plot is giving you the idea that it's well confined inside the core region. One of the results which we have, typical result we have written over here, is that for this given parameters, optimized parameters, you can get the loss of the fundamental mode is 0.07 and not LP11 mode. I'm writing here LP02 mode, 02 mode, because loss of the LP11 mode is crossing the LP02 mode. So we will see the loss between these two modes, and this is going to give you the single mode operation even less than the half meter length of the fiber with the core diameter which is 30 micron and the numerical aperture is 0.16. So this kind of fiber can be really useful host material if you want to design a fiber laser. So fiber laser, if you're designing a fiber laser, there are so many things you have to address upon. One other thing I'm talking about is the host material. So the conclusion we have seen here, if you just look at the conventional optical fiber with numerical aperture of 0.16 and core diameter 30 micron, that will support close to 50 modes. Typically we have written 46 modes, and in our design we are going to get the single. Now I'm coming to some spatial optical fiber which are known as the photonic crystal fiber. What are these photonic crystal fiber? Photonic crystal fiber is also a specialty optical fiber which can categorize into two categories. One is called step index guidance fiber and another one is called rolling fiber or band gap fiber. So what is there in case of photonic crystal fiber? Photonic crystal fiber is having fiber, where you have a solid core here, and inside the cladding you have air holes which is running through the entire length of the fiber. So we can categorize into two categories, in which in one category there is a solid core, and the another category we have a hollow core. In the cladding region, we have the air holes which are set in a particular pattern, and this is running through the entire length of fiber. Now, because of the large degree of freedom, because of the availability of the large degree of freedom in the photonic crystal fiber, this particular fiber has been used and designed to achieve various specialty optical fiber. Few of them I have just shown it here. One is this is a fiber in which you can see, you have the you have large air hole, then you have a small air hole, then again you have a large air hole, right? So this is used for the dispersion compensating photonic crystal fiber. This is a spatial design which is used for the low band loss fiber. This is a highly birefringent fiber. You can see in one direction, in this particular direction, they have taken the large air hole, and in this direction, they have taken the same air hole. So this is creating a difference in the polarization of the X and Y modes. And this is one of the example of the large mode area PCF. So why we have so much application of this PCF? Because it is having large degree of freedom, means you can change what you can change. You can change the shape of the air holes. You can change the number of rings. You can change the pitch of the pitch, means the separation between the two consecutive air holes. Instead of holes, you can use the rod. You can choose the various material. You can also change the shape in which you have arranged the air holes. Rectangular air holes you can take, hexagonal and circular. So because of all this flexibility, it is a very important candidate for the specialty optical fiber. So we have already designed few specialty optical fiber in photonic crystal fiber design, and this two comes under the category which is called the triangular core large mode area fiber, and these two comes under the this particular comes under the rectangular core large mode area PCF, where you can see the air holes and the rods are basically arranged in the rectangular pattern. This is called the asymmetric doped large mode area PCF. Why this is asymmetric? This is asymmetric because in one side we have used the the large air hole, and the another one we have used the rods. So I'll take a few of them, and then I'll move to the other part, which is the dispersion compensating fiber and gain flattening. So this is one of the design which we have used in the PCF, not in the conventional the optical fiber MCVD fiber. This is the photonic crystal fiber. So in photonic crystal fiber, we have a rectangular core large mode area photonic crystal fiber, in which you can see that what we have what we have here, we have a fluorine doped silica. We have given a design of D1, D2 and pitch. What is D1? D1 is basically, you can see here, this is a D1, and D1 is what? It is a fluorine doped silica rod. And then we have a D2, this is air hole. So as I have mentioned that you can use the air hole, but at the same time, you can also use the rod. So here we have used the combination of the rod as well as air hole, which is basically the separation between the two consecutive air holes. So in order to do the analysis of this, what we have done, we have seen the effect of the parameters R1 and R2, where I think earlier mentioned what is R1. It is D1 is equal to 2 times R1. So this R1 is basically the radius and D is the diameter. So we have first seen the effect of this parameter R1, and then the effect of R2 on the on the confinement loss and the effective mode area. The confinement loss we have shown here, and the effective mode area we have shown on the another scale. So what you can conclude it from here, if you just look at the leakage loss is shown with this one, and this one. Here, fundamental mode, first higher order mode, and second higher order mode. What you can conclude that the loss of the fundamental mode is very nominal in comparison to the first higher order mode loss and second higher order mode loss due to the due to the spatial structure which we have given. If you look at the loss of the first higher order mode, again it is showing you the first increase, then it is coming down, right? So it is again giving you this particular peak, and this peak is again because of the resonant coupling of this particular mode with the cladding. So what, while doing the analysis, we have find out that if you take R1 is equal to 1.5, or you take the D1 is equal to 3 micron, the loss of the fundamental mode now is coming so small, 1.36 into 10 to the power minus 2 dB per meter, right? And the fundamental mode is coming close to the 10 dB. So what you can get basically a single mode operation with this parameter in just 2 meter propagation distance. But at the same time, what is the order of area? The order of mode area is coming around 2000. It is coming, if you take R1 is equal to 1.5, it's coming something around 2000 micrometer square. So this is for the R1 parameter. Now what R2 parameter you should take? For that we have done this analysis, and here also you can see the loss of the fundamental mode is always going to be very small, but it is the loss of the first higher order mode and the second higher order mode which is going to decide what R2 value you should take. So from here we have seen that R2 value should be 1.25. If you go into this particular region, the loss of the first higher order mode is always greater than that of something close to 7 micron. It is 8 to 10 micron, in the range of 8 to 10 micron. So you can choose the value of R2 which is close to 1 to 2.5, or D2 value 2 to 5 micron. Next we have seen the effect of pitch parameter, and in the pitch parameter what we have seen that the loss of the fundamental mode is increasing, and again it is decreasing because of the resonance effect. So it is, you have to be very careful while taking this pitch value, because if you are not choosing this pitch value carefully, you need to use your loss of the fundamental mode is going to come down quickly, and for the single mode operation you need to use a large length of fiber. So it is always recommended for given structure, your pitch value should be greater than 90, because pitch value should be less than 19, because if you go greater than this particular value, it comes down very quickly below this. The second point we have seen about the NF, which is the and we have fixed that for NF is equal to 1.435, you will get the maximum mode area with a minimum loss of the fundamental mode. So these design parameters, when they have plotted loss along with the effective mode area, this directly gives you the information that there is a possibility of the trade-off between the leakage loss and the effective mode area. So with the given design parameters, you can find out what design parameter you should go for your particular application. Then we have shown the spectral variation of this loss for the three modes along with the mode area, and you can see the loss of the mode is increasing with the wavelength, which is quite obvious, because as you increase the wavelength, more and more fields are going to spread in the cladding region, and that's why the leakage loss is going to increase. But in the entire spectral region, the loss of the fundamental mode is very small. All right, but it is going to show you the single mode operation in the entire range of 1 to 1.16. Again, 1 to 1.16, with the help of the loss of the first higher order mode, we can decide it. So the another conclusion it is giving you, that it will give you, the single mode operation with a 2.5 meter length of fiber, that you can decide with the help of what is the minimum loss you'll get at 1.0 wavelength of the first higher order mode. The second thing which you can see it from here is that, which I've already mentioned here, the maximum loss is 0.7 and minimum is 8 dB. The second, which you can see it here for the contour plot, this is for the fundamental mode. See, in the most of the power is there inside the core, but if you go to the first higher order mode, you can see most of the field in the cladding region. So that is why there is huge loss in case of this particular higher order modes. Now we'll quickly move to, I will try to skip this one. Just I will explain the principle, that the difference which is here we are getting in case of the other design is that we are using the bend induced mode filtering. Okay, we are going to use the bend induced mode filtering, and for that we have used a large air holes here. And we have some design parameters D1, D2, and D3. D1 is what? D1 is the diameter of large air holes. D2 is the fluorine doped silica, and D3 is again the small air rings holes. So this element design is based on the mode bend induced mode filtering, and this is giving you mode area something close to 1500 micrometer square. And again, we have optimized the parameter, what is the allowed value of D2 and D3, with the help of the simulation results. So if you just look at the straight fiber, you see the straight fiber, the field is looking like this. But if you bend the fiber at some given radius, you see the field is basically leaking towards the bending direction. So this is the another confirmation about the simulation results. So the key results which you can take it from here is that you can get the single mode operation with a very large mode area close to 1500 micrometers square, with a nominal loss of the fundamental. So now till now I have discussed about the use of the leaky designs for the which is one of the specialty optical fiber for designing a host waveguide fiber, which can be used for high power lasers. Now I'm going to talk about another topic. On whatever we will got during the analysis of planar waveguide, which is called resonance coupling. So you know that when you go for any optical communication, you have digital pulses, which is in the form of 0 and 1. When you send it from one place to another, these pulses degrades because of the two spatial effects. One is called pulse dispersion. Pulse dispersion is the broadening of the pulses, and the second one is by attenuation, which is the decrease in the optical level. So I'm just going to address briefly about these two effects and how we can address it. So in pulse dispersion, you know that what is pulse dispersion means the broadening of the pulses. So if there is a broadening of the pulses, which is you can see it here, then there will be a significant overlap between the pulses. And if the overlap is such that you are missing some some of the pulses, then you are going to lose the information. Similarly, if the loss is such that in case of attenuation means the power level of the optical individual pulse will decrease, and if the attenuation is so high that the loss of the individual pulse at the output end is below the threshold. Below the threshold means when at the detector end you are having some power meter, right? And that power meter is set for, it will, if the power of the, the input signal is below some power level, then it is assumed as 0, and if it is above some power level, then it is assumed as 1. So if the at output level the power of each pulse is smaller than that particular threshold power, then the pulse which is actually 1 will be taken as a 0. So in order to address these two problems, you need to come up with some design which can address these issues. So first I'll discuss about this dispersion. What do you mean by the pulse dispersion? As we have discussed, pulse dispersion is because of the various mode which is propagating through the optical fiber. So the different modes takes different time, and because of that there is a broadening in the pulses. There is a broadening in the pulses. This is a sharp pulse, this is a broadened pulse. And because of this, this basically puts the limitation on the data transfer, right? So if you want to have a better data transfer, you need to reshape the pulse after certain propagation distance. So how to do it? In order to do this thing, we should come up with some design which can give you some negative dispersion. You are getting some positive dispersion. So if you are sending the pulses through the optical fiber, which is after certain propagation distance is giving you some positive dispersion, and then you want to make it 0, and you want to reshape the pulse, that you can do by passing through a fiber which is giving you some negative dispersion. So this we have done with the help of a fiber which is called dual core fiber. Again, dual core fiber, we have an inner core, we have the outer core, and then we have inner clad and we have outer clad. Similar structure we have used for the LMA, but here the design are different. Here A value will be small, and we will try to tune them to achieve. Here the inner core is such that it is not giving the multi-core structure, it is just giving single mode, and by tuning this value of n plus the delta minus and delta plus, we'll try to find out the negative dispersion. So how the outer clad which we are taking as a silica. So this silica is basically fixed. Now the refractive index of the core, outer core and inner core can be tailored by this del plus. However, this n minus can be tailored by or can be controlled by this del minus value. So you can increase the refractive index by germanium doping. You can decrease the refractive index by the fluorine doping. This is well established technology in the MCVT. So this design can be used for two design compensation. One is for the narrow band and another one is for the broadband. We'll focus here only for the narrow band. So how to do it, that I have just principle I have mentioned it here. What we have, suppose you have taken A is equal to 1.7, which ensures the single mode operation. Del minus, so silica is there, you control the fluorine doping with del minus is 0.23, and D1 you have taken 15 micron and D2 you have taken 1 micron. So you know that for a fixed value of inner core radius A, this, right, a resonant coupling between the modes of the individual cores, which is the inner core and outer core, this is basically controlled by del plus, del minus, and D2. If you think about this del minus and D2, del minus means this one, and D2, del minus is this one, and D2, this is basically going to control the the effective index of this outer core. However, if you tailor this del plus, this del plus is not only going to affect the effective index of this outer core, but it is also going to affect the effective index of the inner core. Why? Because if you change this del plus, the effective index of this particular layer as well as this particular both is going to change, and that is why we have chosen del plus to optimize this result. And we have For the given structure, these parameters we find out, we'll find del plus is 0.9697 has given the condition of the resonance. So quickly, let me come to this. For this parameter, we have plotted the refractive index, effective index profile, and you can see there is two mode. One is the symmetric mode, and the another one the anti-symmetric mode. At the resonance point, one can easily see that there is a rapid variation in the slope near the resonance wavelength, and this basically leads to the achieve the high negative dispersion, because high negative dispersion is what? It is a double derivative of this one, right? So this is the field profile of the symmetric and anti-symmetric modes. Now this dispersion is basically going to be dispersion at any value of d1 is going to be characterized by two things. One thing is what is the resonance wavelength, and the second point is what is the full width of half maxima of the resonance. So with the what we have seen, that magnitude of the dispersion, which is magnitude of the dispersion with can be controlled by d1, which is basically the separation of this one. So magnitude of dispersion means basically what is the maximum d max you are getting over here. So as expected, you can clearly see the trade-off between the magnitude of the dispersion and full width half maximum, right? So these two parameters, which is the lambda resonance, d max, maximum value of the negative dispersion, and full width half maxima, can be controlled with the d1. And in this particular results, we have shown the basically the variation of d along with the A effective value. So you can see for three different values of d1. D1 is 13, 15, and 17 micron. So you can see for d1 is 13 micron, d max you get something around minus 2500, and the A effective is coming to be 84. For the d1, if you take 15 micron, your d max is coming to minus 6,000. If you take d1 is equal to 70 micron, you can get d max equal to minus 17,000. So this looks that this is better one, but at the same time, you have to be also very much careful about the design parameter, because whatever the design you will get, you will give to the the team which is going to fabricate it. There is some tolerance case also. So you can see the wavelength you are talking about here. If there is a line width of the wavelength is 0.1 nanometer, the variation in the A effective, which we get for this parameter, is 3%. The variation in the A effective, which you have calculated here, is 88 micron. Is there 8% variation is there with 1.1 nanometer line width. But in case of d1 is equal to 17, which is giving a very high negative dispersion value, is showing you at the same time huge variation is the A effective, which is in the range of 18 to 25 micron. So that is why it's better to go for this design parameter rather than this design parameter. So this is one of the application where you can get a very high negative dispersion to achieve to minimize the dispersion which was created because of the propagation. The second part which I have addressed quickly, I will try to finish it, is about the gain flattening. You know that when you send the pulses, you are not sending the pulses at a particular wavelength. You're sending the signal at a different wavelength because you want to use maximum utilize the channel. And these particular, suppose you have sent this signals at some 1.55 and this particular wavelength, different wavelengths you have sent the signal, and you know that all the signal, when they will propagate, they will suffer some loss. How to overcome it? You know that you have to use the erbium doped fiber amplifier. But if you just look at the gain curve of the erbium doped fiber amplifier, this is not same. This is not giving you the same gain for all the signals. This gain is basically going to have different gain at different wavelengths. So now the question comes: if you have a, suppose, say for example, you have 3 wavelengths, and all the 3 wavelengths had suffered from the same loss. Now, if you want to receive the pulse, you want that all the signals should be amplified with the same power. So that can be done if you have EDFA which can give you the flattened gain. So next job is to find out the flattened gain. So there is a, you can classify this in different signal. We are talking about only S-band signal. So in the S-band signal, this is the S-band signal. You can see the gain is something like this. So if you can come up with some fiber which can give you the loss profile which is having the same shape, means this kind of shape, then it will give you the flattened gain. So for that we have used again the resonance structure, and in the resonance structure we have used the inner core, which is not the large core, small core, and then we have coupled the power of this core with the cladding, and because of this it is showing the very sharp change in the leakage loss near the resonance wavelength. So you can see N3 is value, N3 is showing the resonance condition. So if you are away from the resonance condition, you see the spectral variation of the loss is not showing so prominent variation. So we have shown you the variation of the leakage loss, and with the N3 and D3. In case of N3 and D3, this particular value, this curve is matching with the slope of or the profile of the gain profile. So if you use this structure, and so if you have a fiber with this and you dope the fiber with the EDFA and make it an optical fiber, that particular fiber in S band is now going to give you almost flat gain. It is going to give you almost flat gain of the 22 dB. So what I want to conclude that if you do any kind of analysis and you need to analyze this analysis carefully, and that analysis can lead to some new structure, and new structures should be given such that it should be easy to fabricate by your the team which is going to fabricate it, because you can come up with any kind of design, but your design parameters should match with the experimental the tolerance study. So in today's lecture I have tried to give the idea that how specialty design fiber can be used for various applications. Thank you so much. So this is all from my side.
Thank you, sir. Thank you very much. Dear participants, the session is now open for discussion. Dr. Ajeet Kumar, sir, has nicely delivered his talk on the topic specialty optical fibers. If you have any questions, the session is open for discussion. Hi, yes, please. You started. Please unmute yourself and ask the question. Mr. Mayur?
Yes, sir. Can you
please
hear me?
ask. Yes. You are audible.
Sir, are you working in the field of glass fibers only, or you are working in the polymer-based fibers?
See, okay. Good question. See, I'm not doing the experimental part. I'm doing the simulation part. So in simulation part, you have just need to change the refractive index material. So we have done in the polymer as well. You can see this segmented cladding fiber. So segmented cladding fiber is very difficult to design in case of silica. There you need to use the polymer fiber. And yes, you can do it. Just no issue.
Another question was there, sir. I have seen one paper in which they have said about the copolymerization of dye and the PMMA structure. Okay.
Yes.
So in my mind, if we fabricate a fiber which has a two polymers which is copolymerized,
Okay.
in that matrix I want to dope dyes. So will it be possible, or should we have to do some simulation like you are saying before that?
Yes. See, no. Suppose see what kind of help you get from the simulation. Simulation gives you the roughly the idea of the the parameters which should be used for the fabrication. So it gives you the range of the parameters. So it is always good. It is always good to start with some simulation, right? So if you start working in some experimental field and you have some some software, then you should first start with the simulation, and that will give you the better idea. Like in case of one result I've shown you, where we have fabricated the fiber. One of our group have fabricated the fiber, University of Nice. So we have given this particular width you should choose, and this much length you should choose. Otherwise, you are in just in no way that what once for a given design parameters, what length or what other parameters should choose. So it's always better to start with the simulation parameter if you have.
Thank you, sir.
Okay. Well.
Thank you.
Thank you, participants. Now I would like to call upon my colleague, Mr. Atul More, to propose vote of thanks for this session. Mr. Atul, please.
Thank you, sir. Good afternoon, all of you. And thank you again, sir, for giving me opportunity to propose the vote of thanks. So, I would like to thank our resource person, Dr. Ajeet Kumar, sir, Delhi Technological University, Delhi. Thank you, sir, for enlightening us with knowledge and interesting facts about optical fiber. I am pretty sure that, sir, the knowledge you gave us will definitely help us for future references. I would like to thank Dr. Yadav sir, HOD of department and coordinator of FDP for organizing such extraordinary FDP on photonics. Thank you, sir. I would like to thank all the respected HODs, faculty members, resource persons, scholars, and students for present here and paying your attention and the contribution. I also thank to all the members of committee, Dr. Dayanand Raje sir, Swapnil Undalkar sir, Kumar sir, Vijay Zadke sir, and Akshay Mungle sir. Thank you all of you. Thank you. Over to you, Yadav sir.